we can start. We can do a quick intro for our speaker, and then I think we can start the talk. So thank you for joining us, Majid. Majid is an assistant professor at the School of Computation, Information, and Technology at Technical University of Munich, where he leads the chair of AI planning and dynamic environments, and he's also a member of the Munich Institute of Robotics, Machine Intelligence. And Majid, we also are wondering if this is okay to record this talk and
totally
upload it on our YouTube. And yeah, I think with that, we're excited to hear your talk. Thank you.
Great. Thank you very much for inviting me. So today I'm going to be talking about our recent works on basically in the direction of building a foundation model in general for humanoid robots. But I want to motivate a bit first why humanoid robots, while I think nowadays more and more people are actually on the same page. But anyways, robots have been around for a long time in the industrial settings. They have been performing very precise and complex tasks, ranging from car assembly to very precise welding up to basically production lines. But if you look closely into this pictures, you can see that first of all, these robots are doing absolutely repetitive tasks. Secondly, they are not moving around. All of them are fixed pace. And finally, you do not see any human around these robots, mainly because these robots are not actually safe. Nowadays, we see more and more robots out there in our daily, lives. For instance, some of us have a Roomba in the house. Okay, they are doing something. They are not perfect, but still, they have some very minimal, levels of autonomy. Recently, we see more and more quadrupeds and quadrupeds out there, but still, these are far from the picture we have for the future of robotics, where they are supposed to basically help us in very, dangerous, let's say, tasks and somehow some repetitive tasks. So to me, what's required to achieve to basically fill this gap is, first of all, we need to have a general purpose mobility robot, which means that we should have a robot that can go everywhere that human can go. They should be versatile enough, which means that they should be able to perform tasks under these very complex, configurations. They should be dexter in order to basically manipulate objects with different shapes, different physical properties, and so on. And finally, if we are serious about integrating these robots inside our lives, we need to be thinking about accessibility and the social integration of these robots. So for a long time, I've been arguing, I think it's 15 years, that I think humanoids are the, morphology of choice, I would say. But, in the past, I was the crazy person in the room. But actually, I think nowadays more and more people are going toward this direction. This is not that I'm saying that we are there. I think there is a long way to go. But I think at some point, if we are thinking about the general purpose robot, a robot that can really be helpful in our daily life, we should go toward humanoid morphology. But on the other hand, we have seen recently advances in vision language models, action models. They have enabled robots to do tasks that for a long time have seemed very difficult or impossible. For instance, on top, you can see the robot is doing very fine manipulation tasks. So for a long time, again, these have seemed to be super difficult or even impossible to do. Or in the bottom, you can see the robot gets a high-level instruction, and its reason about the environment, generates a long sequence of actions, and basically realize them in the real world. So to just go a bit deeper into what's behind this technology, basically this is the architecture of Pi 0.5. So the idea is this. So basically you would pick a pre-trained VLM, as you see on the left, and basically use them for two main tasks. First is to break down a high-level task to some sub-level task. For instance, we clean the kitchen, and the output would be, for instance, first put the plate in the sink, and then so do that and that until you finish the task. And also, normally some visual question answering is applied to the system in order to help with the reasoning capability. For instance, you would say what's inside this picture, and then the output is a dog catches a frisbee. So these models are nice, but normally they are not good in the context of robotics. So what you would need to do is that you would need to also do some fine tuning with some generated instruction and pictures of robot doing tasks in order to improve its performance. But now, once you have that, the main robotics part is that basically you need to design an action head. And this action head would basically take this subtask prediction from pre-trained VLM and basically transform these to the actions of the robot, right? Normally, here either a diffusion model or any other like flow matching or any other multimodal model is used. And the main question here is that basically where the data comes from in order to go from subtask to basically continuous actions. And this is the main bottleneck at the moment, because we do not have the same range of data that we have, for instance, on the internet for robotic systems. So to just summarize what's happening in this field, so the recipe is this. You would pick a pre-trained VLM, not very big one, something like 3 billion parameter or something like this, and then fine-tune it on some images and instructions of robots. Then basically you need to train a multimodal action model. With what data? Basically, what people do nowadays is that they use teleoperation data. I will talk about it in the next slide. And then you need to fine-tune both models together to make sure that each of these parts know about the other one. You would deploy it in the real world, but normally we will have some distribution shift. The robot fails in some cases. What people normally do is that they would collect more data on those corner cases, add it to the data set, retrain until you get to the basically performance that you would want. So talking about how to collect data for robotic systems, so people nowadays are resorting to the simplest thing you would imagine, which means that the human basically would show the robot on its own embodiment how to do the task. So this is the simplest version of teleoperation. So a human wear an exoskeleton, and basically by looking at the robot doing the task, make sure that the desired task is performed. More advanced ways are using more fancy teleoperation devices that are not so mechanical or based on virtual reality. But when you go to something like a humanoid, because of its underactuated nature, it's not enough to just copy the motion of human to humanoid, because the robot would fall down. So normally a low-level controller is there to make sure that the balance is always preserved while trying to be as close as possible to the motion of human. For instance, here Boston Dynamics, they used MPC as a low-level controller, or for instance, in Unity uses reinforcement learning, pre-trained reinforcement learning for the low-level controller, right? So this is the general, basically, pipeline to generate data. And basically, the problem comes to this, that this is the general motto: in God we trust, all others must bring data. So basically, you would generate all the data, God being here, a neural network and backpropagation, and that's simply all the intellectual things that we are bringing to the table. So I do not believe so much in this picture, while I believe in the power of these large models, but this way of data collection, while very easy and useful, it cannot really lead to something that is super practical, right? Unless you just spend the whole human resources to generate data. And this is basically, these have been proven, I think, with the autonomous driving that has followed the same path. So now we are asking ourselves, can we do better? Can we just, we can always use teleoperation, but, we need to do better, and at least we can augment the teleoperation data or, independently generate data for the robot. So one of the ways that we are pursuing to do that is this 3-block kind of architecture. So we have a task and motion planning framework that I'm going to talk about it. So this gives you an interaction graph between the robot and the environment for doing long horizon local manipulation tasks. Normally, the search space is so big that we can rely on basically the common sense reasoning of the large models, pre-trained large models to give us some proposals. And then once we have it, we can give it to a generalist RL policy in order to basically realize this to the robot. So this is one way of generating data without having access to any teleoperation, demonstration. But the main goal here is not to just generate one motion. The idea is that, so let's say you would ask the robot to bring the laundry basket from top of the shelf. We would like the robot to basically perform the same task with a lot of different ways. And this is very important. Diversity of the data is very important, and that's what exactly we are going for in this framework. So let me go a bit into detail of this whole structure. So task and motion planning, the idea is that you want to provide the robot with a very general instruction, like bring the laundry basket, and we would like to generate automatically the whole motion of the robot. So to give you a bit of notion of what's behind this optimization, so it's only one single giant optimization problem. So we would like to minimize the cost function. For instance, we want, for instance, the laundry basket to be at the end at the desired location. The desired decision variables here we have are two sets. One of X and U, which are basically the joint space states and actions, and S and A, which are symbolic state and action that I'm going to talk about it. So we break down the decision variables and the state and action of the system into two phases. One of them are symbolic, one of them are continuous. So at the symbolic level, we have basically dynamics. So this shows the dynamics at the symbolic level. For instance, in our framework, the symbolic level is contact switches. So for instance, when the robot grasps an object, the objects become part of the body of the robot and the dynamics of the system changes. And now basically we go from one smooth dynamic to another smooth dynamic. And you can see this as a high-level MDP of the problem if you want. And then we have some certain inequality constraint at the level of symbols. For instance, we can say that if the robot has grasped something, it cannot use the same hand to grasp another object because the hand is occupied, right? So these are the symbolic constraints that the problem has. Then at the level of the basically motion, the whole body, we have the physics. So we should have the robot following the physical laws. And at the same time, there are certain constraints. We have torque, joint velocity constraint, obstacle avoidance, and so on. And the idea is that we would like to bring the system from initial state to a desired final state, right? So the idea is that we do not give the robot any instruction how to do the task. We just tell the robot that we want to have the object from point A to point B, and the robot needs to figure out all the sequence of actions in order to achieve that. So that's the whole idea of task and motion plan. So let's go a bit into more detail what's happening there. So basically, let's say this is the example we would like to solve. The robot is there. We tell the robot that basically what we want to have is that we want to have the green box on the floor somewhere, right? So the way we represent this environment, it says that in the initial case, we have the red box in contact with the floor, the blue floor, and with unilateral contact, which means that it's not fixed to the ground. So the green box is on top of platform unilateral. The feet of the robot are in contact with the environment. And this way, we can represent all interactions between the robot, a movable object, and non-movable objects. So this is a simple example of doing that. And the goal is to bring the green box on the blue floor. I mean, you can also give it a location if you want. So this is how the symbolic states and of the whole environment is constructed. And now what we do is that we give this and pass this into our optimization problem, which is a combination of a symbolic planning and a continuous trajectory optimization. And there is a loop carried out here in order to generate the whole body motions. So let's try an example. So let's say for this example, we want to, one sequence of manipulation predicate or a skeleton is right hand grasp the box, the green box, right hand lift the box, place the box on the floor, and basically release the hand, right? This would be a very simple and straightforward set of object-centric manipulation skeleton, basically. Now, what happens is that for each of these subtasks, for instance, right hand grasp box, what happens is that right hand will be occupied, which means that the constraint between right hand and the object will be activated. And the object and environment has also a constraint that is activated. However, other end effectors, other points of the robot, as many as you want, you can define, are free to be chosen. And then, for each of them, we have the same basically structure. Now, what happens is that we can optimize for all other, motions of the end effector. So this is for one of the skeletons of the task. So now you can do another skeleton saying that first grasp the red box, put it in front of the platform, step onto it, grasp it, and so on. So there are a lot of different ways that you can do it. But this way, what we did is that we unified locomotional manipulation through the notion of contact interaction. We represent it like this, and now any type of behavior that is possible can be generated using this framework. So here is an example of type of motions that we are able to generate, right? So here, for instance, some definition. This is a bimanual grasp of the robot, and this is a lift, for instance. This is place, and this is release. So this is, for instance, a simple task can be written down as a 4 sequence of manipulation predicates. And each of them, again, has a graph of interactions. So here, for instance, for the same task, another way that the robot can do the same thing is that basically the only thing that is pre-specified is that, for instance, the left hand grasps the box and put it on the ground. Now the right hand, right foot, and left foot are free to be doing anything that they want. For instance, in this case, the robot is leveraging the effect of the leg and basically its right hand in order to balance its motion to grasp the box and put it on the table. So you can see with this framework, if you let the optimization run over time, it can find the diverse set of different ways of doing basically the same task. Here is another task. We only tell the robot, so the input to the optimization is to put the objects from one platform to the other. That's it. There is no other thing predefined. And basically the robot is coming up with different ways of doing basically this task. And this is very nice because you can generate, not all of them are perfect, but they can be very useful on certain situations because this diversity is important for this foundation. This is another task. So what we tell the robot is that we tell to go up in this environment, right? We don't tell it how to do it. For instance, since the robot joint torques are limited, what it comes up with, basically it reasons about the environment and says I can put the box down and step on top of it and go up. And you can see that the robot can come up with a lot of different ways of doing this thing. So some of them are not fully optimal. For instance, the previous one didn't go up, or some of them are crazy like this, but they are all feasible. And here to show that we enabled all how these constraints are important for reasoning, we just here remove the torque constraint, right? So if we remove the torque constraint from this optimization problem, which means that the robot can generate whatever torque that it wants, the robot will come up with this strategy to go up. So it doesn't need anymore to bring down the box and go up. And sometimes it does also, of course, this crazy stuff. But this is also fine, right? At the end, what we can. So these are physically possible if you do not have torque limits. Okay. So this is nice, but the problem with that Pascal motion planning is that computationally it's very inefficient, and there are a lot of sequences that actually are not interesting. For instance, you can assume that to bring the box on top of the platform, what the robot can do is that, for instance, it can go up the platform, come down, grasp the box, put it there, come back, right? A lot of things that might not be relevant, but it's possible, right? So this is just a huge search space where most of the sequences are simply useless, right? So rather than just relying on search, what we can do is that we can basically leverage the common sense reasoning of the pre-trained large language model or vision language model to help give the task of motion planning some sort of warm start, right? So for instance, here, and this is another work we did. So the idea is that we tell the robot to be as high as possible in this environment. So we started with using a VLM, but the problem is that pre-trained VLMs are not really great for robotics task in general. So what we decided to do at the end is that to build a scene graph representation of the environment, and then add this as a representation to the LLM and ask LLM what is the sequences of action required for this problem to be as high as possible. And then we developed the parsing mechanism that brings this text to basically usable parameter for the optimization. So let's look at an example. So here, for instance, this is the representation of the starting point. G1 is the robot, left hand, right hand, for instance, can be with the right side and left side of the box in contact, and the box being in contact with the ground. For instance, this is one, basically we call it interaction graph. So if the LLM tells you place the box on the ground, this could be an interaction graph for this. So here are two examples. So here is, for instance, the LLM instruction, grasp the box, left hand, and so on. So basically, it provides the set of interactions, and then we can parse this to robot configuration and its interaction with the environment. So this way, the search space, basically, the LLM can give us hints about which parts of the search space are more plausible in order to search for it. So here is an example. So this is the output of the LLM. So for sure, we just give it a dictionary of set of tasks it can do, such that it doesn't say something that is not usable for our framework. So here is the sequence. So grasp two hands with the object, lift the object, place it, and so on. So this is the sequence, and if you apply it, parse it to the optimization, you will end up having this kind of motions. So this is now much faster than just letting the search figuring out all these steps, right? So, but if you look more closely, you can see that actually the object sometimes penetrates with the robot. There is some collision because we did not activate all the collision constraints, because then the problem becomes very non-convex. However, what we can do is that actually there are more information in this pre-trained model that we can use that we did not use in the previous work. For instance, let's say there is a LLM breaks down the task to these 4 steps. Now what we can do is that we can also ask another generative model, for instance, here latent diffusion models, to generate for us a motion of human that does the same task. So human understands the semantics and normally basically gives us a very good set of contact points and postures to do basically this task. And what we do is that we retarget this motion of human to the robot and use this as some keyframes inside the trajectory part, such that we can avoid all the collisions in the robot. So that's the idea of this work. So here we tested this framework on 2 experiments or simulation experiment. In scenario 1 on the left, again, the idea is that to bring down the laundry basket. On the right is to just have the object on the trolley at a certain location at the end of the horizon. And we did an extensive ablation study, and we have shown that actually using our framework on the left, we can have a full collision-free motion, while on the right, if you just naively use the output of the latent diffusion model in the optimization, you end up having very weird motions full of collisions. And we just did an ablation on each component of our framework, and we showed that semantic information is very important, and also configuration of the robot as output, retargeted configuration is also very important in order to have collision-free motions. Okay, this is good. So now what we did is that we found a systematic way to generate different motions for the robot, but this gives you only a trajectory and an interaction graph of the trajectories into the future. But now we need to have a controller to basically track these trajectories. And here, what we wanted to do is that we wanted to basically build a generalist RL policy, in the sense that we want to have one RL controller, right, something like this, such that it can track all the trajectories possible. So then what becomes important is that what's the shared representation between all the trajectories? And one of the information is actually contacts. So if you have an interaction graph, and if you give it to the robot, this information can be very useful in order to build generalist policy. For instance, if you have a manipulation or locomotion, the common ground between all these local manipulation tasks is that the robot make contact and break contact with the environment. And I think this is a very important information that we can leverage in the multitask reinforcement learning setting. And using that, basically, we applied something that we call it contact condition robot policy, and we are able to generate all these different behaviors using a single policy. For instance, top left, you can see that the quadruped is jumping, moving between different gates. Top right, humanoid is doing some random, type of motions, but all of them with one policy, some manipulation and in-hand manipulation. So here again, we are showing that the robot can just switch between different gates, all of them with one single policy. So this is nice. And you can, for a long time, you can do it. And also we have shown that actually, if you just condition the robot policy on the contact, now you can actually put the constraints of the environment inside the contact such that, you have more control over the motion of the robot. So what we did also, we did a comparison, out of distribution comparison with the, then the other representation of the motion, which is a velocity condition policy. So what we did is that we had a quadruped robot trained on to go forward and backward, condition on the right in the velocity and left on the contact. And now we gave some out of distribution goals, and we have seen that actually, contact, those that are conditioned on contact, the policy can actually very well generalize out of distribution, while the velocity condition cannot generalize because it doesn't have this more information about how to do the task. So here we are showing that actually adding this inductive bias of the contact information can help you generalize out of distribution of this training data, which is also very important in the multitask setting. Also, we tried comparing multitask with single task, and we have shown that actually multitask can better interpolate between different motions, while single gate or single task fails. And here are some out of distribution set of motions. We only tried train the robot on, let's say, jumping and trot, and the robot can do a 3-leg jump and hop here, for instance. And this is out of distribution motion. We did also some manipulation tasks showing that the same thing can work on a manipulation. We changed the object shape, and we have shown that contact condition again works better. There is no magic here, right? So you are adding some inductive bias, and this inductive bias helps you to improve weather generalization out of distribution. So that's the idea. So humanoid, again, with this kind of generated motion, and also we did some in-hand manipulation. They are not actually perfect. We didn't try so much to make the motion smooth here for in-hand manipulation. So again, the main idea is that we can train one policy, we have a shared representation, which is contact interaction. And with that, we can basically learn a multitask policy that can also generalize well out of distribution of the trained goals. So this is the general framework that I talked about until now. So we want to generate diverse set of data and make it applicable to the robot. So this is a 3-block general framework. And I think with this framework, we can generate a large amount of data if we are willing to spend computation, right? But one other thing that actually nowadays are becoming more and more popular again is the fact that we can use actually human motion through human videos and so on. So human to humanoid retargeting we can use if we have if we are willing to use a video of human, and then we can use the same generalist RL policy to track those motions. So here is an example. For instance, on the left, you can see this is a SMPL version of the human motion. So this is a kinematically retargeted motion. If you look at the foot motion, the foot is in the air and so on. So it's not perfect, but at least still it gives you a very good hint of how to perform the motion. So here we developed actually physically consistent kind of trajectory optimization, sampling-based trajectory optimization to not only retarget from human to humanoid, but at the same time try to make it physically plausible. So here is the whole structure. What you see on the left is simply an IK-based retargeting, but you can see that retargeting is not perfect. The geometry of contact is not perfect, and this is bad, right? So if you try to track this, the object falls down and you're done. But what we do is that we enable this dynamic retargeting, which makes both the geometry and the physics consistent, and then we show that this helps a lot with the training of RL and also the success rate of the retargeting, and then we can do sim to real. So I think I will not go so much into detail of how we are doing it. So this is the paper actually we are submitting tomorrow to RSS. But again, the idea is that we develop a new sampling-based trajectory optimization that basically takes into account all constraints of the system and makes sure the retargeted trajectory is actually physically and geometrically feasible. And then we applied this framework on some existing data set, and we were able to actually retarget a lot of different behaviors to a robot. And these are, again, these retargeted motions are fully physically possible, right? These are super complex tasks for a humanoid robot, and we can retarget them respecting all the physics, right? And actually what we can do is that we can do some augmentation if we want. We can basically change the object size, we can change object mass, we can use different objects if you can see here. And this is with a single demonstration. So if you have one single demonstration, which can come from even video of human, we can generate a lot of different behaviors that are actually physically correct. And then this can be used basically if you want to generate the foundation model, and then also use to train a generalist RL policy to track that. And here is basically the sim to real transfer of this kind of behavior. So now the retargeted trajectory that physically consistent helps a lot with the training of RL and transfer to the real world for this object local manipulation tasks. So we did a lot of, comparison with the state of the art. We have shown that our retargeting improves a lot the success rate compared to, a spider, which is a recent algorithm last month was published. So our retargeting framework with physics is much more efficient than a spider, much more successful than a spider. It is a bit less computationally efficient, but at the same time, it gives you much more smooth kind of motion. So smoothness of motion is much better. And then also we checked, we compared our retargeting framework success rate with the downstream RL to Omni retarget, which is another state-of-the-art work. So the difference is that Omni retarget only does kinematic retargeting, and we do dynamic retargeting. And you see that with the dynamic retargeting and giving this retargeted value to the RL, you can improve a lot the success rate. Okay, and also the error is decreased and so on. So it's much better as input to the system. We are also trying to using this massive amount of data that we have to train our humanoid VLA or humanoid foundation model. So here, for instance, again, we are building mostly action head, and we are assuming that VLM can give us the sequence of subgoals. So here is the data generated by our framework, the physically consistent, and you can see the ghosted motions are simply the diversity of the data. So here is the first-person view of the robot doing the task. So this is the output, and we can test this on the robot actually. And we are in the process of generating a lot of different data from all human motions out there, and we would like to build to scale our foundation model to a lot of local manipulation tasks. But this is still ongoing work. Okay, so I tried to outline I would say an scalable path to build really foundation model for general purpose robot. But you might say, okay, so that's only that we scale the data and it's perfect because we can have general purpose robot in our home. But I want to push back a bit. So real world is super complicated. Things can go wrong easily, but as soon as things go wrong, we do not have, the robot cannot know what to do. So there's no data in these very weird kind of regimes, right? So one important aspect that we need to take into account and will become more clear in maybe next few years is the safety problem. And we have seen this safety problem, how much it pushed back the deployment of autonomous cars, right? So the technology, I would say technology for autonomous car or self-driving cars have been there for, I would say, at least 10 years. But the safety issue is still there. And that's why we do not see so many of them out there in the streets, right? But at the same time, I want to argue that autonomous cars are much simpler systems compared to a human local manipulation system. So I categorize for myself, the all the kind of safety we need to take into account in general. So the first three are common between a self-driving car and a humanoid robot. So obstacle avoidance, both of them should make sure that there is no collision with the unwanted part of the environment. There is a low-level safety, which means that the control of your motor or actuators or components in your car doesn't go crazy. There is a semantic safety, which means that under different circumstances, you may want to do a different action. For instance, if a robot grasping an object and it's a glass and it's full of water, maybe it doesn't want to pass it over the laptop. But if it's free, most probably it's fine, right? So this is semantic safety, which is again existing. It exists actually in the self-driving car part. But there are two versions, two parts of this safety that are actually special to this case of, let's say, humanoid robot. First of all is fall avoidance. So a car doesn't fall down, but the robot and its object that is manipulating can fall down. So this is another extra safety layer we should have. And the most important one, and the most difficult one, is interaction safety. So cars do not want to make contact with the environment, but any robot that wants to do something interesting in the environment needs to make intentionally contact with the environment. And we need to make sure that, first of all, we do not exert a lot of force such that we break the environment or the robot itself. But if we just do not exert enough force at the same time, we cannot do whatever we want to do. So there is only a small band of desired forces that can do whatever we want to do. And then this is, I think, I would argue, this is the most difficult part of safety that we will need to handle. So we have been doing some early works on the last two parts, which are again special to the humanoid. And I would say all the other three, we can take most of the research done on autonomous driving and using it for ourselves. So fall avoidance here is a simple idea we did a few years ago. But we have improved, but I don't have any result at the moment to show. So the idea is very simple. You need to have some recovery policy that basically you define some unsafe set where the robot is going to fall down. And then you use that recovery policy to take over and bring the system back inside the safe set when it's unsafe, right? And here we use an MPC controller as a recovery policy. And the nice thing is that once the recovery policy takes over and brings the system down, these are actually very nice corner case data that can be used to basically improve the robustness of the base policy. So here the controller is running. At some point it's falling down because of some pushes that is not visible here. And then recovery takes it over, brings it back, and it's added to the data set, and the policy is updated over time. And this we can show that not only does not allow the robot to fall, but it also improves the robustness. So you will have better push recovery capability. So again, these are early the simplified works, but we have made much progress that I didn't still put it here. But another thing, we also did some work actually on the interaction safety. So we did this funny kind of example. We say that the Franco robot will release an egg. So egg, that it's fragile. So we should make sure that when we are grasping it, we do not exert too much force. And here what we did is that we provided something, we wrote down some stochastic optimal control problem that has uncertainty in the contact time, right? And we want to find a strategy that basically is safe in terms of amount of impact between the robot and the environment. So I don't go into detail of this approach, so it's kind of mathematically quite complicated, but it's an efficient way of making sure that if your contact time is uncertain, for instance, you do not know exactly the position of this egg, but you want to make sure that you have a strategy that under different variation of this position, you catch the egg without breaking it. So here, for instance, again, the strategy is general. So here we applied it on a one-leg hopper robot, and there is an uncertainty on the environment, and the robot makes sure that the impact between the robot and the environment is always limited. So this is the orange thing. But also we applied this on this egg catching. On the left, it's an unsafe behavior, and on the right, you can see it's the safe behavior. The robot catches the egg. So I will play it again. So the egg is released. The left one does not take into account uncertainty of the egg, so it's not able to exactly properly grasp it. So it falls down and it breaks. But on the right, basically, by taking into account the uncertainty of the leg, actually the robot is not only able to grasp the egg, but we can also show that actually egg is absolutely intact. So there's no even crack on the egg, which means that the strategy made sure that the impact between the robot and object is within some limit such that it does not break the egg. Great. So these were, again, some early work or preliminary works we were doing on safety, but I think safety is super difficult and it's going to take so long in order to ensure safety of robotic systems. So to wrap up my talk in general, I think VLAs are very powerful, but I do not think using human teleoperation is the right way to generate data to train VLAs. So at least we need to augment the data of the teleoperation with a lot of other model-based data generation approaches. I think automatic generation of diverse behaviors, either from videos of human, or it can be even by search, can really augment the data set, and it's a promising way of building VLAs for humanoid robots. As I said, human videos are a really nice source. So this is also another reason we want to use humanoid, because there is a huge amount of human videos out there on YouTube that you can use. But if you use any other morphology, you do not have such a data for this kind of system. And I think this is a actually huge win for humanoid robots, on top of the fact that they can go wherever human can go. And on the RL side, I think we need to go beyond single task RL and try to really build a single RL policy that can do a lot of different tasks. Again, we talked about contact as being a nice representation, but that's again early work toward multitask RL. And finally, safety guarantees are essential, and there are so many problems of safety that we need to take into account if we are serious about bringing robots to our daily lives. And with this, I would like to thank all my, the members of my team who did all the work. And also, I would like to thank our sponsor. I'm happy to take questions.
Thank you for the talk. I had maybe a quick question to start with.
Yeah.
I was wondering if you could tell us a bit more about how you input the contact information to the policy and overall architecture.
Yeah. Oh, sorry, I stopped sharing. Share it again. So let me go to the slide. So where was it? Yeah, it's here. So basically, as I showed before, either for retargeting or for generating of the motion using our task and motion planning framework, not only we generate the trajectories of the desired behavior, we can also generate the interaction graph, right? Which means what end effectors will go to contact next, and with what kind of interaction it has. It will grasp the environment, it will be unilateral, and so on. And this is basically what inputs the robot to the low-level policy. So the policy is conditioned on the state of the system, but the goal is represented through the contact sequence plus trajectory into the future, right? So here we explicitly condition on the contact positions and timing of all the end effectors. But what we are working at the moment on is that we want to basically pass this information together with the predictive trajectory, right, into an encoder, such that we find an implicit representation that might better encode this kind of. So I do not think, in general, contact is very nice. It's general, but I think at the end of the day, we would like to have an implicit kind of representation that can be shared between all the tasks of the robot. And basically, this is passed to the RL policy. Did that answer your question? Okay, thanks.
Yeah, thank you.
Mm-hmm.
Maybe I'll go next.
Mm-hmm.
In the work that you were talking about failure recovery, uh,
Uh-huh.
isn't the problem of detecting that you're in an unsafe state like already a super hard problem?
Absolutely. But you can always find proxies to that. So the problem of finding the robot will not fall down is called the viability problem, which means that starting from the current state of the system, right, there exists at least one control sequence that the robot does not go to the failed state, which means in infinite time, right? Computing this set is intractable. We cannot solve. But there are very efficient ways actually that we can estimate that safe set, but still it's an open problem, right? So for instance, this is another thing. Mostly for safe set for an obstacle avoidance problem is very easy because you know exactly the boundary. I mean, not very easy, but it's easier than this problem because the boundary of the unsafe set is clear for you, right? But for a fall avoidance, you don't know, so you need to use some proxies. Some heuristic proxies would be, you need to make sure that the base doesn't go height doesn't go below something. These are heuristic. But if you want to systematically and formally compute that, this is called the viability set. And the way to compute it to me is to just offline generate a lot of trajectories and then basically build a big delta set of safe and unsafe behavior and just learn this set. That would be the way to go to me. But still, this is the next step. So at the moment, still we don't know, given a safe set, how to make sure that the system doesn't fall down. That would be the next step to learn the safe set at the same time. But that's also a very interesting problem.
Got it. Thanks.
Mhm.
Yeah, hey Majid, I've got
Right.
like I don't know, a bunch of high level questions.
Yeah.
Maybe I'll start with a bit of background.
Mm-hmm.
Because you're using VLAs in two different, like you talked about being able to generate data for VLAs, but then you're also using VLAs to kind of warm start optimization systems.
But
Maybe.
that was not VLA, that was a pre-trained VLM, right? So if I go
Mm,
back, so I know I do not use, I just tell the VLM or LLM even, um, tell it just give me a sequence of text. That's it. How to do the task, right? And this would be the sequence of tasks. So, for instance, this is the sequence of text. So we do not have a VLA for sure. If we had a VLA, we didn't need to do any of these things, right? So here is a pre-trained VLM. They are very good in terms of common sense reasoning, right? This we know. And this will help reducing the search space of our task and motion planning. But still, the optimization need to be run such that this is projected to a whole body motion of the robot, right? And then this data will be used, and you can have a lot of diverse set of data. And then this data can be used to train a VLA for humanoid, right? So for instance, let's say now you generated the data. What you do is that if I go to this slide, yeah, here. So these are the data generated on the left. What you do is that you roll out in the simulation, you collect first person view of the sensor and so on. And now what you can do is that you have the sensor information plus the motion, the action, and then you can train a VLA because now this is exactly the data that you want to train a VLA, you see?
yeah, okay. But then maybe getting to like an extension of this, sort of like what's the next step? I guess my real question is whether or not you think VLAs will be perfect enough someday after all this data generation that you won't need them. Um, but I think like even if you used a VLA, like it'd be a great way to like init the action space, like even for the optimization. So use the VLM. Do you see us using a VLA in the future, or will to init basically optimization process? Or do you think there'll be a bunch of stuff that we can just use VLAs for?
So I should again distinguish between VLM, pre-trained VLM, and VLA. And again, VLA, the most important part is the action head. So we need to generate data to build the action head, which is the, let's say, diffusion policy, if you want, which is conditioned on the wide range of different tasks, right? This we don't have any data for. So that's the thing. We need to generate data for this system. But now if we do not have demonstration, right? We do not have if we assume we do not have the video and so on, we need to solve this super high dimensional non-convex search plus gradient-based optimization, right? But what you could do still for generating data, right? You can ask, because we wrote down the problem such that it's a language friendly, right? So our logic is represented as language. As you see here, the representation is a function of language. Now what we can do is that we can ask VLM to give us text step-by-step instruction, and we can parse that to the, to our optimization problem. And this again gives us a way to generate data. So here we use, let's assume it's LLM, because that's easier. So LLM helps us to break down the search if you do not have a demonstration. This is one way of generating data. If you have a demonstration, or if we only rely on the videos, perfect. Then what we need to do is that we need to, and actually I see this to be very promising. This works super well. And actually we have been generating a lot of data, especially if you look at here in the bottom. So this one, we are changing the mass of this object from 0.5 to 8 kilos. And we can generate physically plausible motions to do that. Here with the one single demonstration that we had, we are generating motions to do this kind, all kind of objects, you can put it there. On the left, you can see that we are changing mostly the size of the object. And all of them, again, came from one video demonstration. And now we can see how much you can scale. So I see that the retargeting is a very, it really can give us a big step toward the data. But you might think, oh, there are certain cases that we may not have demonstration, and you might want to generate data for those kind of regimes, right? And that would be the search algorithm. But we are moving more and more toward this, because this seems to be super promising for data generation. But still, you might also think that for a long horizon task, so for instance, if you ask again, we do not have those kind of long demonstrations, right? I mean, if you have it, perfect. If you don't have it, then still you need to break it down to small ones, and at some point stitch them together. And that might still need the task and motion planning or something like this framework, such that you abstract the sequence of logic-based task or something like this. First grasp this, then put it there, and so on. So stitching also them together is something I do not think you just give a small motions, right, to VLA, and it will figure it out how to do the long horizon. That would be very surprising. It might be able, but it would be very surprising. So still you need to also generate some long horizon motions. With this, it's a bit difficult. Here, for instance, for 10-second motion is perfect, but if your motion needs, 100 seconds of, sequence of actions, there are a few tasks that you need that, but still. So yeah, I'm still thinking, but the thing that really made me change a lot my mind again is this human to humanoid motion generation, because this really makes things easier. And nowadays with parallelized simulation, we can use this sampling-based optimization and really get super high quality without single penetration, without anything physically correct kind of demonstration. And this can be helpful for training one single policy for RL, and at the same time a diffusion policy if you want to generate trajectories for RL, or you can think about just building one action head, right? If possible. I think it's difficult for underactuated systems like this. For a manipulator, I think it's possible. For this is a bit difficult, but that's also another possibility, that we just build one diffusion that gives text of pick the object, put it there, and output simply the action joint PD targets, for instance, right? This is much more difficult. At the moment, we are taking two components. One is a diffusion policy that gives trajectory, and then RL just makes a robust policy around this trajectory, tries to track this, right? And this retargeting, physics retargeting, is useful for both of them. You can train the diffusion for that, and also training RL with this diverse set of trajectory helps you a lot.
That makes sense. Yeah, okay, thank you.
No problem.
Hi, thanks for the talk. I have a question about the sort of sim to real gap that you see. You mentioned it briefly, but yeah, I guess the data pipeline collection that you're proposing is in sim. So I wonder like how you see that trade-off with having more data, but not real world.
So to be honest, again, that's another reason that I'm sold to the idea of the retargeting, because in the past we were thinking so much about training an RL from scratch, right? Training RL from scratch is very difficult, and normally what happens is that RL just exploits all imperfections in the simulation because simulations are wrong and so on, and sim to real becomes so difficult. But once you have a desired trajectory only to track, first of all, your reward terms become only 3 terms, not more, right? Tracking the object, tracking the robot, and some simple contact reward. So 3 reward term, that's it. And now actually the same domain randomization for all of them, right? Because here you are not doing some motion that is not basically, that is very weird and it's very difficult to go to the real world. Actually, your motion is inherently, I would say, in the right area of the state space. And so to just summarize what I said is that having trajectory as input to RL helps with the not having a lot of reward term, and also it helps with the with the small domain randomization being enough to transfer different motions to the robot. So actually, it's so I do not think that RL only would solve these problems. RL is very powerful in building robust policies because you can do randomization, right? But the problem is that just searching in the space of policies through RL is such a difficult problem, right? So until now, we've been shaping reward all the time. I do not believe in that. But if you have a trajectory, actually this unifies a lot. So if you have a desired trajectory as input, right, this unifies a lot and the structure, and it's really makes the sim to real much easier and much more standard because the motions are actually very clean. They are not shaky. They are not, high frequency. So sim to real becomes much easier. So we didn't do anything special for sim to real, really. It's just a minimal randomization of, let's say, a bit of contact and a bit of joint friction and so on. That's it.
Great, thank you.
Hey, I had a quick question.
Mm-hmm.
You mentioned really quickly that, or you sort of glossed over that. You mentioned VLMs, like the video models weren't really great, and so that's why you resorted to using LLMs. Could you elaborate a little bit on that?
Yeah. So I talked about it twice actually. The first one was here. So when I was talking about this here, right, I said you pick a pre-trained VLM, right, and then connect it to action head. The problem is that pre-trained VLM do not work super well when you are using a robotics task. So you need to really fine-tune this on some robotics task. But what you are referring to mostly is, I think, this one. This one here. So the ideal case would be that you give this picture to a VLM and tell it to give us a sequence of text to do the task, right? That would be the ideal case. But the problem is that if you give this to the VLM, no chance it can work because it doesn't know, it's a huge amount of information here. You need to understand the context, you need to understand the segmentation, you need to understand a lot of things, right? But the thing is that if you just give a privileged set of information, so we assume that we know the segmentation of everything and give this to LLM, which means that you break down understanding of the context and picture and so on, and generating sequence of reasoning through text, if you just separate them, it works much better. That was basically our understanding. Because VLMs, if you give this to a VLM and tell it, give us the sequence of action, at least the ones that we work with and the open source ones, they don't work well at all. But for instance, if you use LLM, for instance, if you use DeepSeek, it's very good for reasoning. We use the open version, very good for the reasoning. And then, but now what you need to do is that you cannot give it a picture, so you need to represent somehow this image, right? But you can think of this representation not being so difficult, right? Because nowadays there are very powerful models that can actually do this for you. For instance, if you care about segmentation, the new SAM3, video model or something, they're super good. So there are certain components that are really good. I think it's better if we just a bit more specialized things here. We generate we have one module that understands this picture and then LLM to just do the reasoning rather than doing VLM together. I foresee that at some point VLMs become so good that we don't need that. But at the moment, they are not good, so they cannot do reasoning. So that's why we had to do this.
Okay, thanks.
For questions, we could stop here, but let's thank the speaker one more time.
Thank you.
Thanks a lot. This is great.
Thank you for having me.
Yeah, no problem. Thank you. Take care, Majid.
Thank you.